Hi friends, in the last lecture we have discussed heat exchanger analysis by Effectiveness-NTU method. In this session we will solve some numericals pertaining to the same. We know that NTU method is preferred when outlet temperatures of both the fluids are unknown. The first question is, in a chemical plant, 16.5 kilograms per second of a product at 650 degrees Celsius with the specific heat capacity 3.55 kilojoules per kilogram degree Celsius is used to heat 20.5 kilograms per second of the incoming fluid from 100 degrees Celsius with Cp 4.2 kilojoules per kilogram degree Celsius. If the overall heat transfer coefficient is 0.95 kilowatts per meter square degree Celsius and the installed heat transfer surface area is 44 meters square, calculate the fluid outlet temperatures for counterflow and parallel flow arrangements. In this problem, the outlet temperatures of the fluids are not given, and in fact we are asked to find out the outlet temperatures of hot and cold fluids for parallel and counterflow arrangements. Here the fluid with the inlet temperature 650 degrees Celsius is the hot fluid, and the mass flow rate of the hot fluid is 16.5 kilograms per second, and the corresponding specific heat capacity is 3.55 kilojoules per kilogram degree Celsius. The fluid with 100 degrees Celsius is the cold fluid. Cold fluid inlet temperature is 100 degrees Celsius. Mass flow rate of the cold fluid is 20.5 kilograms per second, and corresponding specific heat capacity is 4.2 kilojoules per kilogram degree Celsius. In addition to this, the overall heat transfer coefficient of the heat exchanger is given as 950 watts per meter square degree Celsius, and heat exchanger area is given as 44 meters square. We are asked to find out the outlet temperature of hot and cold fluid for counterflow and parallel flow configurations. In this problem, effectiveness of the heat exchanger is not given. To determine effectiveness, we should know heat capacity rate of the fluid and NTU. Heat capacity rate of the hot fluid CH is given by m dot h into Cph. Substituting the values, we will get CH as 58,575 watts per degree Celsius. Similarly, heat capacity rate of the cold fluid Cc is equal to m dot c into Cpc. We will get the value as 86,100 watts per degree Celsius. Now we know that the value of Ch is less than Cc, that is heat capacity rate of the hot fluid is smaller compared to that of the cold fluid. So heat capacity rate of the hot fluid Ch is taken as C minimum and Cc is taken as C maximum. Once you know C minimum and C maximum, the heat capacity rate ratio C can be calculated. C is equal to C minimum by C maximum. Substituting the values, we will get C as 0.68. In addition to this, you can calculate NTU, which is given by UA by C minimum. Substituting the values, you will get NTU as 0.71. We know that effectiveness of a heat exchanger is the ratio of actual heat transfer rate to maximum heat transfer rate. The maximum possible heat transfer rate Qmax is given by expression 2. Actual heat transfer rate in terms of the temperature change experienced by the hot and cold fluid is given by expression 3. Substituting the expression for actual heat transfer rate and maximum possible heat transfer rate in equation 1, effectiveness can be expressed as a function of temperature difference experienced by the hot fluid and temperature difference experienced by the cold fluid given by equation number 4. First, we will consider counterflow arrangement. We know that in a counterflow heat exchanger, effectiveness can be expressed as a function of NTU and heat capacity rate ratio capital C given by the expression. It is 1 minus exponential of minus NTU into 1 minus C divided by 1 minus C into exponential of minus NTU into 1 minus C. Substituting the values of NTU and heat capacity rate ratio, we can get effectiveness for the counterflow arrangement as 0.4435. From equation 4, effectiveness of a heat exchanger can be expressed as a function of temperature difference experienced by the cold fluid, and it is given by this equation. In this equation, all the variables except Tc2, that is exit temperature of the cold fluid, is known. So substituting all the values, we can get the exit temperature of the cold fluid Tc2 as 265.87 degrees Celsius. Similarly, from equation 4, we can express effectiveness as a function of temperature difference experienced by the hot fluid by this expression. In this expression also, all the variables are known except TH2. Substituting all the values, known values, we can get TH2, that is exit temperature of the hot fluid, as 406.07 degrees Celsius. Similarly, for parallel flow arrangement, effectiveness of the heat exchanger can be expressed as a function of NTU and C by this expression. Effectiveness is equal to 1 minus exponential of minus NTU into 1 plus C by 1 plus C. Substituting the values of NTU and C, effectiveness can be obtained as 0.415. As discussed earlier, effectiveness of a heat exchanger can be expressed as a function of temperature difference experienced by the cold fluid given by this expression. In this expression, the only unknown is Tc2. Substituting all the known values, Tc2, that is exit temperature of the cold fluid, is obtained as Tc2 is equal to 255.21 degrees Celsius. Similarly, effectiveness in terms of temperature difference of the hot fluid is given by this expression. By substituting the known values, exit temperature of hot fluid is obtained as TH2 is equal to 421.75 degrees Celsius. In this problem, the objective was to determine outlet temperature of hot and cold fluids for counterflow and parallel flow arrangements. For counterflow arrangement, outlet temperature of cold fluid is obtained as 265.87 degrees Celsius and outlet temperature of hot fluid is 406.07 degrees Celsius. For parallel flow configuration, outlet temperature of the cold fluid is 255.21 degrees Celsius and outlet temperature of hot fluid is obtained as 421.75 degrees Celsius. It is also observed that under similar conditions, for counterflow heat exchanger, outlet temperature of cold fluid is always greater than the outlet temperature of the cold fluid from a parallel flow heat exchanger, whereas outlet temperature of hot fluid will be always smaller than the outlet temperature obtained from a parallel flow heat exchanger. Next problem. Two fluids A and B exchange heat in a counter-current heat exchanger. Fluid A enters at 420 degrees Celsius and has a mass flow rate of 1 kilograms per second. Fluid B enters at 20 degrees Celsius with a mass flow rate of 1 kilograms per second. Effectiveness of the heat exchanger is 75%. Specific heat of fluid A is 1 kilojoules per kilogram Kelvin and that of fluid B is 4 kilojoules per kilogram Kelvin. Determine 1. The heat transfer rate. 2. The exit temperature of fluid B. This is a problem pertaining to counter-current heat exchanger, that is a counterflow heat exchanger. The inlet temperature of fluid A is 420 degrees Celsius, which is greater than that of fluid B, which is 20 degrees Celsius. So, fluid A is the hot fluid and fluid B is the cold fluid. Mass flow rate of the hot fluid is 1 kilograms per second and corresponding specific heat value is 1 kilojoules per kilogram Kelvin. Mass flow rate of cold fluid is 1 kilogram per second and specific heat capacity is 4 kilojoules per kilogram Kelvin. Effectiveness of the heat exchanger is given as 0.75 and we are asked to find out the heat transfer rate Q and exit temperature of fluid B, that is exit temperature of the cold fluid, that is Tc2. We have heat capacity rate of the hot fluid CH is equal to m dot H into Cph, which is obtained as 1000 watts per Kelvin. Similarly, heat capacity rate of the cold fluid Cc is equal to m dot C into Cpc, which is 4000 watts per Kelvin. Heat capacity rate of the hot fluid is smaller compared to that of the cold fluid. So Ch is taken as C minimum and Cc is taken as C maximum. Now, heat capacity rate ratio capital C given by C minimum by C maximum is obtained as 0.25. Now the first task is to determine heat transfer rate. We have effectiveness as the ratio of actual heat transfer to maximum possible heat transfer rate. Substituting all the values from this equation, we can get heat transfer rate Q is equal to 300 kilojoules per second. The next task is to find out exit temperature of fluid B, that is exit temperature of cold fluid. We know that effectiveness of a heat exchanger can be expressed as the temperature difference experienced by the cold fluid by this expression. In this expression, all the variables are known except Tc2. Substituting all the known values, exit temperature of fluid B, that is Tc2, is obtained as 95 degrees Celsius. That is, in this heat exchanger, the heat transfer rate Q is obtained as 300 kilojoules per second, and exit temperature of fluid B, that is cold fluid, Tc2 is equal to 95 degrees Celsius. Next problem. A simple counterflow heat exchanger operates under the following conditions. Fluid A, inlet and outlet temperatures are 80 degrees Celsius and 40 degrees Celsius. For fluid B, inlet and outlet temperatures are 20 degrees Celsius and 40 degrees Celsius. The heat exchanger is cleaned, causing an increase in the overall heat transfer coefficient by 10%, and inlet temperature of fluid B is changed to 30 degrees Celsius. What will be the new outlet temperatures of fluid A and fluid B? Assume capacity rates are unaltered by temperature changes. This is a problem pertaining to counterflow heat exchanger. The inlet and outlet temperatures of the fluids are given. Now it is mentioned that the heat exchanger is cleaned and overall heat transfer coefficient is increased by 10% by cleaning. Moreover, the inlet temperature of fluid B is changed to 30 degrees Celsius. We can consider this problem consisting of two cases. Case 1, that is heat exchanger before cleaning, and case 2, heat exchanger after cleaning. Here we are asked to find out the outlet temperatures of fluid A and fluid B after cleaning. Since outlet temperature of both the fluids are unknown, we have to use Effectiveness-NTU method to solve case 2. But the problem is that to solve case 2 using Effectiveness-NTU method, heat capacity rates of the fluids and overall heat transfer coefficient after cleaning are required. The heat capacity rates are mentioned as same as in case 1, and overall heat transfer coefficient is increased by 10% compared to case 1. So first we solve case 1 using LMTD method to get the values of heat capacity rates and overall heat transfer coefficient. Using these values, we solve case 2 by Effectiveness-NTU method to get the outlet temperatures of fluids A and B. This is the methodology that we use to solve this particular problem. In this problem, the inlet temperature of fluid A is greater compared to that of fluid B. So fluid A is the hot fluid and fluid B is the cold fluid. For case 1, inlet temperature of hot fluid is 80 degrees Celsius. Outlet temperature of hot fluid is 40 degrees Celsius. Inlet temperature of cold fluid is 20 degrees Celsius. And outlet temperature of cold fluid is 40 degrees Celsius. Overall heat transfer coefficient for the case 1 is taken as U1. For case 2, the inlet temperature of cold fluid is changed to 30 degrees Celsius. Inlet temperature of hot fluid is 80 degrees Celsius. And overall heat transfer coefficient is increased by 10% compared to case 1. So U2 is equal to 1.1 into U1. We know that hot fluid is fluid A for case 1 and cold fluid is fluid B. Temperature change experienced by the hot fluid is TH1 minus TH2, which is equal to 40 degrees Celsius, and temperature change experienced by the cold fluid is TC2 minus TC1, this is equal to 20 degrees Celsius. We know that the fluid that undergoes maximum temperature change possesses minimum heat capacity rate. In this case, hot fluid experiences more temperature change compared to that of cold fluid. So heat capacity rate of hot fluid will be minimum. So C minimum equal to CH and C maximum equal to CC. Applying energy balance to the heat exchanger, we have Heat lost by the hot fluid is equal to heat gained by the cold fluid. That is Ch into delta T hot fluid is equal to Cc into delta T cold fluid. We know that Ch is C minimum and Cc is C maximum. So we can write this as C minimum into delta T hot fluid is equal to C maximum into delta T cold fluid. Rearranging this expression to form C minimum to C maximum, we will get heat capacity rate ratio in terms of temperatures of hot and cold fluid at inlet and exit for case 1. Substituting the temperature values, we will get heat capacity rate ratio C is equal to 0.5, and this heat capacity rate ratio is same for case 1 and case 2. Now we can express heat transfer rate Q as Ch into Th1 minus Th2, that is in terms of a temperature difference experienced by the hot fluid. Q can be also expressed in terms of LMTD as U1 into A into theta m, where U1 is overall heat transfer coefficient and theta m is the LMTD. We know that Ch is C minimum. Now rearranging this expression, that is taking Ch to RHS and the theta m to LHS, we can write U1A by C minimum is equal to Th1 minus Th2 by theta m. U1A by C minimum is nothing but NTU corresponding to case 1. So we can write NTU1 is equal to Th1 minus Th2 by theta m, where theta m is the LMTD. LMTD for a counterflow heat exchanger can be obtained from this expression. Substituting the values of temperatures, we will get LMTD theta m is equal to 28.85 degrees Celsius. Substituting the value of theta m, Th1 and Th2 in NTU1, we will get NTU1 as 1.386. Now we will consider case 2. Here, outlet temperatures of both the fluids are unknown, so we have to use Effectiveness-NTU method. NTU for case 2 will be obtained from NTU 1. We know that for case 2, heat capacity rate C is equal to 0.5 and area of the heat exchanger will be constant for case 1 and case 2, such that A1 equal to A2 is equal to A. NTU for case 2 is given as U2A by C minimum, where U2 is the overall heat transfer coefficient corresponding to case 2. We know that U2 is equal to 1.1 U1. So NTU2 can be expressed as 1.1 U1A by C minimum. U1A by C minimum is NTU1. So NTU2 is equal to 1.1 NTU1. Substituting the value of NTU1, we will get NTU2 is equal to 1.525. The expression for effectiveness of a counterflow heat exchanger in terms of NTU and C is given by this relationship. Substituting the value of NTU and C, we will get effectiveness of the heat exchanger as 0.6957. Now we know the expression for effectiveness in terms of temperature change experienced by the cold fluid given by this expression. Substituting all other values, we will get Tc2, that is exit temperature of cold fluid B, as 47.39 degrees Celsius. Similarly, effectiveness expressed in terms of temperature change experienced by the hot fluid is given by this relationship. In this relationship, all the variables except Th2 is unknown. We can find out Th2 from this expression by substituting all the temperature values. Th2 is equal to 45.22 degrees Celsius. Now, outlet temperature of cold fluid B, that is Tc2, is equal to 47.39 degrees Celsius, and outlet temperature of hot fluid A, that is Th2, is equal to 45.22 degrees Celsius. Now we discuss a special case of counterflow heat exchanger. For a counterflow heat exchanger, effectiveness is given by this expression. If heat capacity rate ratio of a counterflow heat exchanger becomes 1, that is C minimum by C maximum approaches 1, then effectiveness of a counterflow heat exchanger becomes indeterminate from this expression. In such condition, we apply L'Hopital's rule. That is, we differentiate numerator and denominator with respect to C separately and apply limit until a realistic solution is obtained. By doing so, effectiveness of a counterflow heat exchanger for C equal to 1 is obtained as epsilon is equal to NTU by 1 plus NTU. It is all about this session. Thanks for listening. We'll meet in the next session. Till then, bye.